All right, hello class. This week is week 11, and we are going to go over chapter 9, which is atmosphere processes or atmospheric processes and severe weather. So, anything that has to do with tornadoes, thunderstorms, droughts, blizzards, ice storms, foggy weather, heat waves, wind and sandstorms, or dust storms, all of those things are going to be considered as severe weather. In fact, hurricanes, cyclones are also part of severe weather, but because their processes are so large, those are going to be covered in chapter 10. So again, hurricanes and extratropical storms are going to be covered in chapter 10. But apart from that, we're going to cover most of the other types of severe weather in this chapter. So it's a pretty heavy chapter. So keep up, and we'll do the best to get the message through. So what you're seeing in this picture is really a composite of, 8 or 7 pictures of a tornado that is forming in Kansas. So you see at the beginning is not yet a tornado, it's just a funnel cloud, as you're seeing in the picture on the left over here. And slowly it becomes a tornado as soon as it hits ground. The tornado goes through different stages. So here it almost looks like it's gonna decline and no longer have its tornado-like nature. But then it picks up again and it becomes in this cylindrical kind of funnel shaped as you're seeing it to the right. So it picks up strength and it could go on for many kilometers onward. So it's just kind of a really cool picture. It was probably taken by some of the tours that do tornado seeking, literally, and we'll talk about that later on. Okay, so before we get into the specific types of severe weather, we have to undergo this understanding of energy, types of energy, heat transfer itself, and a few just atmospheric processes themselves. So energy might be kind of a hard concept to understand at first, so let's go through a few of the key words that will build up to it. So force is going to be a part of energy that we can feel. Force is measured in newtons, as you might know. And then work is going to be, or work is being done, I should say, as energy is expended. So when you actually have energy in place and you're using it as a force, then you have some work that is being done. Work itself is measured in joules. And a joule is going to be equal to 1 Newton applied over a specific squared distance, if you would. So, so basically, if I am pressing on, let's say, the door of my house in order to get in, and I'm pressing kind of hard, but not really, maybe I'm just laying my whole body against it, but I'm not actually pushing it, then I would be applying however heavy I am, that I would basically put into newtons, and then that would be applied over the overall area of my door. So that kind of gives you an idea of how work is defined. And then the rate at which work is actually being done is the power. So it's going to be basically however many joules over however much time you're spending. So let's say that same idea, I'm still laying my weight against the door and I'm doing so until the door opens. The door is never going to open if it's lodged, if I'm just laying my weight, but maybe it's a very old door, so the hinges will give in or something. So if I continue to lay my weight against that door for, say, maybe a minute, the hinges will give enough that it will open. So the power is going to be that amount of work, so again, my body on the door for a minute, which is 60 seconds. Okay? So power itself is going to be measured in watts, which, as you're seeing there on the slide, is going to be joules per second. 1 watt equals to 1 joule per second. Okay? All right, so just to give you kind of like a few things on data, a thunderstorm itself is going to spend 1 trillion joules. So it uses 10 trillion joules, sorry, as work that is being done every time the thunderstorm happens, pretty much. And that's just an average. And then in comparison, a hurricane spends about 100,000 times the power of, that the thunderstorm had. So if a thunderstorm spent 10 trillion joules, then the hurricane spends however much that is, 100,000 trillion joules, which is ridiculous. So there you go. That's just kind of an idea of how big these types of events are. We talk about quantities that are being spent on energy that are going out of the earth and are coming in, then we're going to see a few different things. So by human consumption, a year, we spend about 440 exajoules. And as you're seeing there, an exajoule is 10 to the 8th power. So I think that's close to a trillion. Yeah, close to a trillion. No. Let me see. Let me do the count for you guys real fast. Maybe I can type things. So it's going to be, what is this? 100 millions is an exajoules. So we're spending 440 million, so 4 billion, 4.4 billion exajoules, or joules, sorry, of human consumption a year. That amount of energy is leaving the system by our consumption. And then the internal heat from the Earth due to radioactive decay, as we're seeing, inside the Earth, basically ongoing and being heated from the inner core all the way up to the surface, is about 2 times as much as we, as humans are consuming every year. So we are actually getting a lot more energy input just from the overall radioactive decay that is ongoing from the core. And then, just to compare that, the amount of solar energy that is coming into the Earth just from space is about 10,000 times more than what we consume every year. So, based on that, the solar energy itself is going to be what mostly heats up our planet, which is pretty cool to think about. So although the internal heat of our planet is still more than we as humans, create basically, it is really solar energy what heats up our planet. And that's why planets that are pretty far from the sun are so cold, right? And other ones that are closer to the sun are so hot, because it's just a massive output of energy. It's ridiculous. So those are kind of things to keep into perspective. So the internal, before we move on, I wanted to mention a couple things. So the internal heat energy from the Earth itself may be a little bit underrepresented, and it is very hard to really know this data exactly. We don't have a great understanding of it yet, and it is hard to measure. So my graduate research actually dealt with heat conduction through soils, and I'll talk about this a little bit more later. But it basically tried to determine accurately what the heat was that was being driven from the soils into the surface boundary was going to be at areas with hot springs. So it doesn't necessarily just apply to areas with hot springs. Yes, you're going to have more heat conduction. More heat is going to travel from the hot springs to the soil in hot springs, but heat is going to travel through the soils regardless of the specific temperature that it's at. It's still going to travel through colder soils from warmer ones. So my research basically found that using different tools, you're going to get very many different measurements about this heat that is leaving the Earth. So if we are using different measurement tools, then you might be getting different representations of the heat that is coming from the inside of our Earth. So that number that they give you there of what it would be 8.8 billion, joules that are coming from within the Earth may be a little bit underrepresented or overrepresented depending on the tools that they use. So I can't tell you what they used because they didn't really tell us in the chapter, but just so you know, this may be slightly over or underrepresented. All right, so in terms of what types of energy there are out there, your book says there are three there's really mostly two, and then the third one that they're giving you there is just an example of them kind of working together. So the first step is going to be the potential energy, or also known as stored energy. So an example of potential energy would be something like water held at a reservoir behind a dam. So you know that if the dam were to be open, open basically, and the water let through the dam, then that water would be actually in motion. So there's a lot of potential energy stored behind that dam. That water could create a lot of energy, basically. The kinetic energy is going to be energy that is actually in motion. So using the same example, once the water that was behind the dam was released and it starts to accelerate slowly, then it's going to create that energy, and slowly, or I guess faster and faster, as it continues to accelerate and flow down, it's going to pick up energy. So I hope that makes sense. Again, potential and kinetic energy. So here in your book they say also about heat energy, which they say is the energy from random motion of atoms and molecules. So basically energy that is being done by the different motion of those molecules and atoms as they move around a specific space as they have. So based on this heat energy, there are two types of heat that they relate. One is going to be called the sensible heat, and then the other one is the latent heat. So the sensible heat is going to be heat that we can feel, such as temperature that is being transferred from one object to another. And usually this temperature can be measured through a thermometer. So anything in terms of just putting a thermometer under your tongue, that would be sensible heat, because it's something that you can feel. You can feel it with a thermometer, you can feel it with your finger if you were to do that. It can be felt. The latent heat is going to be the amount of heat that is being absorbed or released when a substance changes phases. So as you're seeing there in the graph, things have latent heat right before they change phases. So in the beginning of the graph, as you're seeing down here, things are solid. You're having probably some sensible heat as the solid still goes from, say, I don't know, -20 degrees Celsius to 0 degrees Celsius, where you have latent heat, where that change of phase is happening, going from solid to liquid water. So again, the latent heat is that amount of heat that is either absorbed or released, depending on what chemical process you're undergoing, or physical process, as the substance itself changes from phase. So same thing happens when you have something go from liquid to gas or gas to liquid. So when you have evaporation or you have condensation, you have an amount of latent heat that is either being absorbed or being released, right? So it's absorbed when you go from liquid to gas, when you evaporate things, and that latent heat is released when you go from gas to liquid or you condensate things, okay? And then the sensible heat would be checking the specific temperature of that liquid as it goes from just turning from solid all the way to just about to evaporate. So hopefully that's understandable. If not, again, let me know, please. So in this slide here, we see, or in the picture, we see an example of the three types of heat transfer that we know today. So one of them, or the most obvious, if you would, is going to be conduction. So conduction is going to be heat flow through a substance from high temperature to low temperature. So you're always going to get the heat transfer from hot to low. So that's something to remember. So conduction has to happen when two things are in contact. So as the image is showing you, conduction is happening from the hottest part of the pot to the handle. So it has to be a material that is touching each other, if you would. Certain materials are going to be better for conduction than others, and some of them are going to be more repellent, if you would. So I'm going to go ahead and stop this video because I'm almost out of time, but I will continue to tell you about conduction and the other two types of heat transfer in the next little video.